and the harder you're punching your GPS receiver, the harder it has to work. So it's better to have it in a softer environment, like being carried higher up on your body, than smashing it into the ground mounted to your foot. So be aware of that. Another dirty little secret is that GPS receivers, as they're designed today, are not actually doing the correct sort of maths at the moment for where we often try to use them with our wearable devices, which is in cities and indoors. So the maths going on inside a GPS receiver is based around the assumption that the signals are coming in a straight line directly from the satellites out in the open. That's how the system has always been designed. Now, as soon as you start doing really difficult stuff, like this chap that was running his marathon on his balcony at the start of the COVID era, you've got this interesting situation where you're only revealing a very narrow strip of the sky to the GPS receiver, and the signals are not easily punching through the ceiling that this guy's running under and the walls that the building he's kind of on the balcony of. And what will actually be happening here is that signals are bouncing off the building on the other side of the road from behind him, in effect, and coming, into his balcony from completely the wrong direction, with lots of extra path length. And that path length is critical. That's how the GPS receiver is actually calculating where you are. And you can actually see from this chap's Strava record, you can see the size of his actual balcony on that building versus the positioning fixes that were being generated during this run. And these huge errors, over hundreds of meters of error, are being caused by a combination of both only having a small number of satellites in the fixes, but also that the path lengths have gone much longer paths than they should have done, much longer paths than the receiver is calculating and taking into account for, because they're bouncing off stuff. And that's one of the challenges that needs to be overcome for accurate GPS positioning near buildings and in cities. And then one of the other little dirty little secrets is that many devices are talking about providing low power and having low power modes, but the trade-off here is often a trade-off in the precision, either in the update rate or in other ways of how accuracy can be generated inside that device. And so one of the simplest ways to reduce the battery consumption of a GPS chip is, instead of having it provide a measurement once a second, have it provide a measurement once every 5 seconds or every 10 seconds, which of course then reduces the overall understanding of the distance traveled and when you change speed and all of these sorts of things. This little movie is showing off the difference in precision between a normal GPS chip running as fast as it can, if you like, highest rate it can update, which is once a second. That's the little red dots you can see there. And the blue line is our detailed human motion modeling technology, which I'll talk about in a moment. And you can see the great difference between not only the update rate, but also the actual accuracy, as Henry here runs inside this interior part of a train station in London. And we can accurately reproduce the trajectory, but normal GPS feed cannot, because again, the signals are bouncing around too much inside that environment. And if you've not seen that movie already, it's on our website, the full movie here of us running through London with our software running on a running watch. So what can be done about these sorts of problems? So the first problems I mentioned were around that very low cost GPS receiver and the fact that the signals bounce around so much. And so one of the really powerful things about these very low cost, high volume GPS receivers that we have now embedded in so many of our devices is that they have a large software defined component to them nowadays. So go back about 10 years and the GPS receivers that we bought as consumers were just dedicated for purpose chips. They were burned fuses in silicon. They couldn't be reprogrammed. And once they'd been designed and burned in the factory as a silicon substrate, that is all they did. They couldn't be changed. They did their one job well. Nowadays, you can actually software upgrade, change bits of the code that's running on these chips. And that's what we do. We actually upgrade parts of the software in other people's GPS chips in order to boost their performance. And one of the most important things that we do is we solve this particular problem of understanding when signals have bounced and they're coming in from the wrong direction. And our software, the supercorrelation technology as it's called, for the first time allows a receiver to actually look in the correct direction for the satellites and to ignore signals that are coming from the wrong direction. So we take it from this sort of nasty, difficult scenario where multiple copies of the same signals from a given satellite are bouncing lots of times inside urban canyons between buildings and are all coming to you somewhere inside this canyon. We go away from this nasty problem and have something that looks a bit more like this, where we're just paying attention to a straight line between you and the satellite. And we can actually see through 2 layers of brick. We increase the sensitivity of that receiver such that it can see through 2 layers of brick, which means we can see through some light buildings. But in general, we're only gathering data from the direction that the satellite is in. And the only other way you can have this capability today is with a $10,000 military antenna called a controlled radiation pattern antenna. They only come in green, they're very heavy, and they're massive. You wouldn't want to go carrying one of these things around on a run. But built inside here are lots of little antennas, and it actually has a way of looking effectively in a physical manner, looking in different directions to just gather data from the direction that each given satellite is in. And our software goes inside the chip inside a normal consumer device and provides the same sorts of capabilities. It can also lock onto energy coming from just particular directions. And that's unique to us and is a game changer for GPS and provides all of these new performance capabilities. And this is actually what it looks like kind of under the hood inside that super correlating GPS chip. So each one of these circles that I'm showing you here, you can imagine it being like a radar plot of the whole sky above your head. And each one of these is numbered. So that's satellite number 1, satellite number 3, satellite number 14. The little red dots are the positions in the sky that each of those satellites is actually in. And all of the colors is showing you effectively a heat map of the energy coming from lots of different directions. So if I pick on satellite number 22 here, that was directly overhead. And you can see there's very little energy coming from any other directions than this glow coming from the right kind of strip of the sky above us. White is the hottest amount of energy, and it's all coming from the correct kind of place. But if we look at satellite number 23, the hot spot is nowhere near where the satellite truly is in the sky. And what's happened in this instance is that satellite number 23 was just disappearing behind the edge of a building at that moment there. And we're able to isolate and find and just extract the weak remaining bit of energy that's just coming through the edge of that building just as it's disappearing. That's what this faint green glow is in the correct part of the sky. This bright white stuff here, that's 100 times louder than the weak remaining weak signal coming through the building. And that big glow on the north side of us was the signal bouncing off a bus or a large metal object or something shiny and highly reflective north of where we were. And normal GPS processing inside wearables today just hoovers up all of this, and it all gets corrupted and mixed up and causes all sorts of horrible positioning errors. But our supercorrelation technology isolates just the line of sight and keeps track of just the data we want that's coming straight from the satellite. The next big step is when you would actually start to use all of the measurements you can see in these plots combined with an actual 3D building model of the city and match all of the extra signals to the surfaces they're bounced off, add that extra path length into the maths inside the receiver, and turn your, in this instance, kind of 6 satellites into maybe 60 measurements, all being matched to buildings and being used to further improve your understanding as to exactly where you are in a city. That's still a little bit way off, but it's on the roadmap, that combination of our measurements with 3D building models. So that talked about the first 2 problems, the very low cost GPS chips and the problems of the signals bouncing around inside the cities. Going to cover just a little bit about the ability to provide very high precision measurements still on these low cost wearables. So the traditional way that the sensors inside wearables was being used for understanding your motion through space, so using the accelerometer, the gyroscope, the barometer, etc., was to make quite simple measurements with them. So the most basic of all is looking for when the accelerometer reading exceeds a certain value and simply declaring that that was probably a footstep. And so you can count steps in that manner. And the simplest early wearables that were just doing step counting were just counting the bashes of an accelerometer inside the wearable device. But instead of taking just a very simple step counting approach, you can combine all of the measurements. The sensors can make measurements at sort of 1,000 measurements per second, but they typically run at about 200 samples per second, these sensors. You can take all of the measurements and craft together with a human motion modeling suite a reconstruction of how the device has actually moved through 3D space. And that's what we're doing here. You can effectively see every bump and wiggle as that smartphone there on Henry's arm is carried on its journey up the stairs and around the corner. And so this is a 3D reconstruction with centimeter level precision as to how that device has moved through space. And this is an example of the same setup, just pounding around a running track. So the wiggles you're seeing there are again the kind of wiggles of Henry's arm as he runs, but you can see the consistency of, in effect, every step on that journey round and around the running track is being accurately reproduced at 200 measurements per second. And the key thing is that in certain circumstances, this processing can be lower in power than GPS processing. So when GPS has a good clear view of the satellites, it's in its kind of lowest power mode, what's called tracking mode. But when the signals are not available or very weak, all the knobs get turned up to max inside that receiver as it desperately tries to hang on to the signals. And it will often go into a search mode where it's effectively searching lots of different options to try and find the signal again. And it's that search mode, that acquisition mode, when GPS becomes very power hungry. And in these sorts of instances, like in this part of this promo video where we're actually inside and running, that's when the GPS will be at its most thirsty, trying to hang on to the signals. But processing the inertial data with human motion modeling is a much lower power way of understanding your journey through space. FIFA actually have defined a kind of test that wearables must pass if they're to be accredited and can be have this kind of FIFA stamp of approval for being used as a sports fitness wearable. And this is one of the tests for that accreditation process, running a series of shapes in a certain dimension layout with a mixture of walking, jogging and sprinting. And this is actually our reproduction of that FIFA accreditation test. I think this was a wearable mounted between the shoulder blades on this particular test, but it can be mounted in various places on the body, and our human motion modeling system can still reproduce the behavior that the human went through as you move through space. And again, you can kind of see the fine detail, every little bump and wiggle of every step that was taken during that sprint. And the speed is being returned here as well. This is coming just from the inertial data, the accelerometer and the gyro data. It's not actually using the GPS data to make those estimates of speed. And that is to do with the human motion modeling technology being able to relate patterns it's seeing in the inertial data to speed and the actual direction. So in other words, if you're running forwards, backwards, sideways, etc., all of that can be unpicked from the sensor data. So I think I mentioned this along the way, but I'll just make it clear, of the two sort of products that Focal Point is pushing out into the world, they sit at different places inside your device. So the supercorrelation technology that changes how GPS data is processed and locks on properly to the signals, that has to go inside the GPS chip. So we partner with the manufacturers of GPS receivers in order to deploy this technology with them. And we can bring these significant performance benefits, as well as this whole new way of kind of grabbing GPS data and actually showing where it's coming from and making use of the signals that have come from different directions. Detail is the name of our human motion modeling system. So that can be applied to wearables today, regardless of whether it's an existing design GPS chip or a new supercorrelating chip. Obviously, combining both together is best, but Detail can be deployed at the moment in the application level, and provides that level reconstruction of human motion through space. So the only company that we've been able to publicly announce our work with so far is u-blox, who've signed some of our intellectual property to be developed into their next generation chips. So they're one of the providers of the supercorrelation new GPS technology. There are some other companies that we're working with at the moment at various stages of integration, but we haven't publicly released who those other companies are yet. So certainly get in touch if you want to find out more about when u-blox's supercorrelating chips will become available. And I'll happily take any questions you've got on any of that at all. Thank you very much. Don't know if John is there or if I finished too early.